Yeah, good morning, sir.
Yeah, so let's start. A very good morning and welcome all the audience, our members, non members, even someone from outside as well, to this important 6G Leadership Tech Talk on the topic 5G Advanced, Trailblazing the evolution towards 6G. And today we have a very eminent speaker, Mr. Mahesh Basavaraju ji. He is a distinguished telecommunication professional with more than 20 years of experience. But what is more important that test instruments, ODM, OEMs are always ahead of technology than others because then only we design certain things. So I'm sure that Mr. Mahesh Basavaraju will be able to cover the topics which is very important for academia who are doing the research as well as industry who will be subsequently going for the products. With this, I welcome you to this. And since I don't see my chairman in this users, so I directly request you to start your presentation and we'll be just giving you the rights. Thank you for accepting our invitation. Asta, can you give the rights for Ajay? Okay, I have made you presenter. So now you over to you
Okay.
and thank you all, welcome you all, and good morning, good evening. Namaste.
Yeah, thank you, sir. Thank you very much for this opportunity. Thank you. And good morning to all the audience here. And welcome to this presentation on 5G Advanced Trailblazing, the evolution towards 6G. So I'll quickly share my presentation. Yeah. So give me a quick shout out if you can see my presentation already on my screen. Can you see my
Yes,
presentation?
yes, we can, but please make it.
Okay. Yeah, I'll do that. Yeah.
Thank you.
So
Please go
again,
ahead.
thank you very much for this opportunity. Thank you, sir. So for the next 45 minutes or 50 minutes, I'm going to talk for about all the technology candidate research candidates which lead to shift G technology. So with that preface, let's look at where we are coming from. Like say, for example, IMT 2030 is work for 6G, leading the vision and the mission for 6G, what this new technology should look like. And here, if you look at the capabilities, so there is already some framework led about what should it be in terms of capabilities. Here you see storage, user data rate, spectrum efficiency, connection density, mobility, latency. This is something which we have all been working starting from LTE. And 5G, we have had some goals. And in 6G, these capabilities will be further enhanced, which means it will work on the already laid out foundation by 5G in 5G Advanced, and then further this will be enhanced in 6G. And in addition, 6 more new capabilities have been added for IM30. So these include coverage, that is ubiquitous connectivity, sensing related capabilities, is all pervasive, and then sustainability. All these future networks should keep sustainability from the starting, from design. It should be sustainable, interoperable, and also positioning is going to have a more impact in the future generation networks. Yeah. And then if you look at the usage scenarios was called the first technology built around use cases. So we all know about this triangle. So on one hand, we have the enhanced mobile broadband. During the last tech talk by Ericsson, they also mentioned about how successful one of the use cases like fixed wireless access, which comes under the EMBB umbrella, is success. And this will further evolve into immersive communication. And then we had ultra reliable low communication, which will enable smart factory like use cases. And then this is again going to further evolve as hyper reliable low latency communication and massive machine type communication. So here the connection density will further enhance. We'll see millions of devices served within per kilometer area. So that is the massive communication. So these are all natural evolution of the use cases which were already started in 5G, 5G advanced. Now in 6G, we see three more additional cornerstones, especially if you look at integrated sensing and communication. So this is a completely new feature where networks will be able to provide sensing features in addition to communication. And then AI will be tightly integrated into the network architecture so that you can use AI as native in the future generation networks. And then we have also the ubiquitous connectivity powered by non-terrestrial network. So connectivity wherever you go, anywhere on the globe. So that is the mission where we are working towards connecting the unconnected. So with these goals, let's see what is the timeline now. So for example, timeline right now we are in 2026 and we have started to work on release 20, and release 20 onwards now we see two branches. One branch, the blue one, where the 5G advanced work will be further carried out and followed up with. And then in addition, we have a parallel branch wherein we will look into the 6G study items in all the different round 1, 2, 3, and 4 groups. So here the 6G studies will go on until the mid of 2027. And then we will have as an outcome of the 6G studies the technical reports based on which the 6G normative specification will start forming from release 21. And then by end of release 21 we should have the specifications based out of which we will see the first 6G devices maybe by 2029 2030. So that is the timeline we are looking for the first 6G networks and the devices. And of course, for any technology to be evaluated in a real scenario, you need some big events. So that is where we have the Los Angeles Summer Olympics, where you will have trial networks, where you will test the capacity of 6G devices as well as 6G networks with all the new features which will be explored now, that is in release 20. Yeah. So that is the main events. And in between, we also have the WRC 27 planned in 2027, where some of the spectrum related decisions will be taken. Like, for example, we are talking about non-terrestrial network. And we have some interesting spectrum aspects. So say, for example, this 7.125 gigahertz to 8.4 gigahertz, which is the golden band. So how that will be allocated for 5G or 6G. So this will be decided in the WRC 27, and which is well within 1 year time frame from now. Yeah. So with that, let's look into the main technology pillars. Say, for example, if we have to classify all the research candidates which will shape the 6G. So here we start with, say, undoubtedly, the whole industry is interested in non-terrestrial network. That is ubiquitous connectivity powered by non-terrestrial networks. So this will be one feature which is going to be worked on. And then we have immersive communication with the use of new classes of devices which are extended reality capable. And then we have AI. I'll also talk about some AI RAN related stuff, how we are enabling the industry with AI RAN. And then some new spectrum, and also what is called the massive MIMO now will evolve into giga MIMO or gigantic MIMO or extreme MIMO, as it is called in some of the countries. And then we will have integrated sensing and communication, which is a game changing feature. And in addition, we have some other features like enhanced duplex, open networks, and distributed computing, which is some kind of open RAN, and then photonics and security and trustworthiness. There is no doubt from day one, 6G networks have to be secure by design. So that is what we will look at as key technology pillars. Now I will dive into some of these features in the consequent presentation and throw some light about what are the challenges in we could probably see as part of this deployments, 6G deployments. Yeah. So first of all, let's look into non-terrestrial network. So non-terrestrial network, although it was introduced in release 17 of 5G Advanced, yeah. So here the release 15 and 16 already had it as a study item, and uh, we already had as part of the study item, the industry was looking into the channel models, how this base station, when it is moved to the satellites, what will be the different channel conditions. So this is not the terrestrial network channel conditions, but it will be different. So these CDL and TDL fading models, the channel models were discovered or studied on. And then the frequency aspect, whether we are going to work with FR1, FR2, how are the different frequencies suitable for non-terrestrial network, the different device types, constellation, the satellite constellations who are interested to offer these services, deployment scenarios, and also different PHY aspects, and so on, were studied as part of release 15 and release 16. And starting from release 17, 5G started to enable NTN, non-terrestrial network. Yeah, 5G is not offering non-terrestrial network, but it's enabling non-terrestrial network. Non-terrestrial network satellite communication has been there for long, but as a silo, as a separate industry, satellite communication was serving their own customer base, and then terrestrial networks their own customer base. Now we start from 5G, how these both worlds can co-work or convergence of these two worlds. So that is the essence here. So 5G started to enable NTN starting from release 17, and then yeah, as usual, the initial challenges like how do we deal with the timing, long time delays between the UE and the base station, which is now on the satellite, and the Doppler shift as the satellite is continuously moving. So, what will be the frequency shift and its effect on the operation communication system in the communication system? So, this is what we looked into in release 17. And then during release 18, some new frequencies like say beyond 10 gigahertz was looked into. Some new UE categories like VSAT category UEs were looked into, and then mobility scenarios. Release 19 was the time when we started to look into regenerative payload. I will describe these in the further slides. What is the difference between transparent payload and regenerative payload, and then what does that mean? And then release 20, that is where we are currently now. And especially here in the non-terrestrial network scenario, if you look at, there is particularly a dependency on the GPS signal, the GNSS signal. So the UE has to determine its own location first using GPS, and then the relevant satellite constellation, which will be visible to this UE from this location, and how this constellation will change over a period of time. So for all that, it is dependent on GPS, GNSS signal. So now this is kind of because if somebody jams the GPS signal, GNSS signal, or if somebody can spoof the GPS signal, then the whole communication system, which is relying on GPS, can be brought down or can be misled. Yeah. So that is where we are looking at in release 20 to make the NTN operations GNSS free or more resilient for GNSS dependence. So that is the story with release 20. And then release 21, which is 6G, as I told, by 2030, we should have a unified 3D, three-dimensional network. So terrestrial network, non-terrestrial network, all working together as one network, providing a seamless experience for the user. So that is the ambition with NTN. And then, in that regard, let's look into the four different kinds or paradigms of NTN. So, first one is satellite communication, non 3GPP. So, if you remember, the first disclosure or the first services were available, say, from Apple devices. They started to work with Global Star and then provided some means to have the SMS being sent. Yeah. So whenever there is no coverage from the terrestrial network, Apple devices could have services from Global Star satellite constellation, and it enabled the Apple device user to provide some emergencies SMS. Yeah. So this was the first of its kind, non 3GPP, non 3GPP, because the way the phone connected to the base station or to the satellite is proprietary in nature. So that is not dependent or on a technology defined by 3GPP. So that is why it's non 3GPP satellite communication. Yeah. And then because if there is no standard, so every operator, every device vendor might come out with their own partnerships, and then the industry might fragment, right? So that is a challenge. So that is where 3GPP stepped in and said, okay, we'll define these NTN services within the 3GPP specifications, and starting from release 17. So we started with NB-IoT. NB-IoT is a legacy technology already there, and then we use this NB-IoT based NTN. So NTN, non-terrestrial network, but using NB-IoT and addressing, of course, the IoT use cases. Say, for example, for livestock monitoring, or say tracking the vessels traffic, or say, for example, remote monitoring of the wind um, engines, and so on. So here it's based on best effort, quality of service, and delay tolerant. So very basic IoT use cases can be achieved with this 4G NB-IoT based NTN. And then future, this is going to evolve into what these red cap devices, reduced capability devices defined in 5G, will be part of this IoT based NTN. Yeah. And then we have NR based NTN, that is the 5G based NTN. So here we need the UE, the protocol stack has to be changed, and also you need to take care of several other things like coexistence. How do we take into account the extended timers, the delays, and how do we deal with moving base stations? So this will be addressed in case of NRNTN, and then here maybe you can achieve a better throughput compared to NBNTN. In NRNTN, maybe a voice call or a data transfer can happen. So, meaning to say, new extended use cases can be addressed with NRNTN. And then in the meanwhile, we have something called as direct to cell, wherein the satellite network operator can provide services phones. That is the phones which you and me are using today, may it be some LTE phones or 5G phones. With I can use that to connect to the satellite services offered by the satellite network operator. So here what happens, it could be in what spectrum does it operate. So one is the satellite network operator can operate in his own mobile spectrum, mobile satellite spectrum, the spectrum which has been allocated to the satellite network operator to provide services for mobile broadband. Yeah? Or he can have an understanding or a cooperation with a mobile network operator, and they can do a spectrum sharing. The mobile network operator will say, okay, whenever I don't have a coverage in certain areas, then satellite network, you provide the service, and in the backend I'm going to share all the details of the user and the user location, etc., the system information block to you in a one-to-one manner. Like, say, there is a close collaboration, the satellite network operator, the mobile network operator, they have to work in tandem, in close cooperation, to get this information, provide the system information block to the UE, and provide complementary services. So this is in a way to come to the market early enough. So here, as you see in NRNTN, you need changes on the device side, you need changes on the base station that is going to reside in the satellite side. So meanwhile, while this is available, in the meantime, direct to cell is an opportunity to capitalize on the market, come to the market, offer services to the market. So these were the four paradigms. And now looking at the different deployment scenarios. So here we have deployment scenarios, transparent and regenerative. What is the difference in case of transparent payload? So here we have the terrestrial network, the G node B connected to the core network. In addition, now we bring in the NTN gateway into picture, and then there will be a feeder link which feeds this, that is the air interface signal, onto the feeder link transparently, just a repeater, and then sends it to the satellite. The satellite will amplify, repeat the same signal on the user interface to the UE. Then this will be the serving link. So what happens here in the NTN, the payload is a transparent repetition. So it takes the data from the feeder link, no processing, nothing. So it will just repeat it on the UUU, the serving link to the user, and it is a transparent payload. Yeah. So this is the first implementation where the satellite on the payload side, it's just a repetition of the signal received from the feeder link onto the service link. And then we have the other, which was a regenerative payload, which was introduced in release 19. So here, if you see the base station, we have moved it now to the satellite. So this could be parts of the base station. Say, for example, now with disaggregated RAN, we have the RU, DU, and the CU. So we can just decide to move the RU and the DU, which does the decoding, the processing inside the satellite. So the RU and the DU will be stationed on the satellite. Of course, on the satellite, there are size limitations, power limitations, weight limitations, right? So here, depending on the trade-off, so if you put the entire base station onto the satellite, maybe it's much more closer to the UE, you have less latency, but you need power for all the processing activities, you need storage, the weight of the satellite will increase, and also there is a limitation on the size. Yeah. So that's where there are different approaches. You could have the RU and the DU on the satellite and the CU still on the ground. So the difference would be then, say for example, if you look at the transparent mode operation. So here, for every packet which has been sent by the UE, it goes to the satellite, back to the gateway, and then to the core. So the C plane latency will be higher. But regenerative, so here, because the processing happens in the satellite, the latency will be lower, but then you have to look into how you are going to provide power to the base station which is inside the satellite, and also the other limitations. Say for example, if you are serving hundreds of UEs, and then the feeder link between the gateway and the satellite, so what should be the capacity of these front haul? That has to be calculated. Yeah. So this will be the trade-offs and advantages, disadvantage of the two deployment scenarios: transparent payload and regenerative payload. So now we talk about non-terrestrial. We are moving the base station to the satellite. So what are the implications? So of course, coming from a test and measurement background, there are several. Say, for example, the satellite. So when the signals are beamed from the satellite, so how do you define the coverage area? So in case of terrestrial network, between the borders of a country, you can adjust the antenna tilt, and then the power, output power of the base station. Thereby, you can restrict the transmission within the country's coverage, the borders. Yeah. So now in case of satellite, how do you do this kind of planning? So that will be a challenge. And then the other challenge would be the coexistence. So here, say for example, the downlink signal from the terrestrial network can interfere with the downlink signal which is coming from the satellite, NTN. Here, the downlink signal is the aggressor, and the downlink signal from the non-terrestrial network is a victim. Yeah. So likewise, we have 6 different scenarios like downlink signal, uplink signal interfering with uplink signal, and many more scenarios. So all this has to be now taken care while you're doing the network planning. Yeah. In that respect, there are some new KPIs or metrics being defined. Say, first of all, the power flux density. Power flux density is the summation or aggregation of the power with respect to a reference point on the, so the aggregation of all the power transmitted on the different beams from a satellite. So this will be my power flux density. So if there are 2 or more satellites, then the aggregated power from all the different satellites, that will be my equivalent power flux density. So new metric. And likewise, transmit to the base station, which is on the satellite. So here, this is my wanted signal, yeah, to the satellite. But then there is an off-axis antenna gain. That is, this could cause an interference for the signal transmitted by the neighboring satellite. So these are some of the additional considerations you have to look into. Yeah. So for measuring this, so when it's transmitting in the wanted signal, now we take a hemisphere slice, and then we have to do the measurement for different angles. So this is the impact on the test and measurement part. So when you are defining or designing a base station which will fit into the non-terrestrial network, so you have to look into all these coexistence and interference possibilities, and you have to do more testing. So that is the message ultimately. And then if you look at the protocol wise, the protocol stack which is on the base station as well as on the UE side, now you have changes because you're now dealing with delays and the Doppler shift, which is with respect to a base station which is much, much, much far away. For the UE, it's communicating with the base station not at 10 kilometers away, but maybe 1,000 kilometers away. So that is where you have to now design the MAC layer with additional considerations in terms of the timing constraint. Like the hours with the device was 16 HARC process was running in parallel. Now with NTN, it will become 32, doubled. So the software on the UE should allocate instead of 16, 32 HARC processes. The timing advanced value, because of the long distance between the UE and the satellite, the base station which is on the satellite, the timing advance will be very high. So that has to be compensated for. And also the mobility scenarios, the NAS and the RRC scenarios, there are much more to test compared to a UE which only supports terrestrial network. Yeah, more number of scenarios. So if you take, for example, one use case like the handover. So what used to happen in the traditional networks? So here, if you see, a phone used to send the measurement reports, and the base station would say how often this measurement report should be sent. And then the base station receives the reports from the UEs, the different phones, and then it makes a handover decision based on this measurement results. And it would contact the target base station and say, okay, now there is a UE which will come and admit to your network. So be ready. And then the decision is conveyed to the UE. The UE will then send a RRC connection reconfiguration complete message to the target base station saying that, okay, now the handover is complete. Remember, the decision is with the base station. Now, in case of non-terrestrial network, there are two challenges. One is, unlike the terrestrial network where signal from one base station was going down, the signal from the other base station was going up, and after some threshold is reached, a report will trigger that handover action. So here there is considerable change between the power levels from the different base stations. But in NTN, the signals will not have that dramatic change between the signal levels received. say, for example, if you look at the GPS signal strength, most regions all over in different localities will see minus 110 dBm. Yeah. So that is where you don't see that significant RSRP change. So that is where now in NTN we have something called as conditional handover, wherein the conditions will be defined and will be communicated to the device under test. It can be a phone or a UE or a car, and then this device will evaluate continuously the conditions mentioned, and then when the condition is met, so what are those conditions? So here you have a glimpse of what those conditions look like. So it can be based on the device distance. It can be based on the timer. Say, for example, once you see the signal from the base station, you are viewing this signal from base station one, and then after some time, say 2 minutes later, this satellite would have gone, and then the new satellite will arrive. So after 2 minutes, it's time for you to change or request the handover. Or that is a timer based, right? Or it can also be distance based. Like, for example, I've come from this reference position when I received my conditional handover configuration, and after so much distance, and when I'm so closer to the second reference point, so now is the time I do a handover to the target base station or target satellite. So you are continuously verifying if you are meeting these conditions which are mentioned in the conditional handover. Yeah. So continuous evaluation of conditions, and the decision now is with the UE when to do the handover. Those are some of the complexities you might have to take into consideration when we say terrestrial network and non-terrestrial network integration and seamless connectivity or ubiquitous connectivity is easier than done. It's easy to say, but a lot of complexity behind. Yeah. So this was one example I wanted to give. There are many, like, say, for example, starting from the components you use, the antennas, the ground station component and system configurations, the planning with respect to the satellite monitoring, link planners, and the devices. And post deployment, you also have to do the field testing and quality of service monitoring. So there are different areas where you need to look into. So all of that, only when you can master all these areas, you have a seamless ubiquitous connectivity. So that was about real network. And let me move on to the next feature, which is immersive communication. And immersive communication, here we are looking at, say, devices which are, say, capable of supporting extended reality. So here we are talking about, so in my previous traditional networks, LTE, 5G networks, we were mostly concerned about my phone's throughput, the transmission power, the spectrum emission, and so on. But now with such extended reality devices, you need to take care of something called as motion to photon latency. That is, I wear the device, and then as I move my head, my image also should move without significant lag. If there is a lag, then there is a degradation of the quality of experience. And then very soon you will throw that device away because you feel motion sickness. Yeah. So that is where you have to look into some additional testing requirements there. So this is a typical test bed where you have a base station simulator in the test bench inside a lab, and then you have these kind of devices mounted on a positioner which will move through the different degrees of freedom, and then you will see if there is a degradation in the packets traveling from the server to the client which is on the device. Yeah. So that was in brief about the extended reality, the metaverse. Then we talk about AI run. So AI run. So uh, in 5G, artificial intelligence was used mainly for automating some network functions and so on. It was an afterthought. It's not native. It's not by design we are using artificial intelligence. But artificial intelligence can be used in a lot of things on the device, on the base station, on the radio access network. And here, thanks to the AI RAN Alliance, where we are also part of this alliance, we can put those into three different baskets. One is AI on RAN, providing AI services for which you need a high performing network. So that is the essence. And then AI RAN, use AI to bring in spectral efficiency, operational efficiency. So that is the second category where I use AI to improve the different blocks within the transceiver chain of a radio access network. And then the third one is AI and RAN, that is about AI, how my network can have a shared infrastructure for network functions, the radio access network functions, and also for the AI. AI needs compute power and so on. So, how can I have a shared infrastructure between radio access network and the artificial intelligence? Computing requirements, so on. So this is the three basket. How we can classify AI and RAN. So here, this is quite similar to, like, say, for example, a phone which is capable of offering Gen AI services. So all those, now we have new KPIs, new parameters. So earlier it was only throughput. Now we also have to look into, like, say, as soon as I type in some text into the prompt, it becomes a token. Tokens are the basic units which is processed within the AI world. And now everything is converted to tokens, and I need to check how many tokens were generated by this device. And once I started asking some questions, what was the time taken for the server, which is on the edge, to respond? So, time taken to respond to my first token. So, that is the parameter. So, earlier we had the ping, so to measure the latency, now it is the time taken to respond to my first token. So those are some new KPIs which you will see as part of AI PCs or AI enabled devices. So this is the same which I mentioned just now: tokens taken per second, consumed per second, and inter token latency, time to first token, and so on. So now let's look into one of the important aspects, that is AI for RAN. Yeah. So AI for RAN. So how do we use AI, artificial intelligence, to enhance the efficiency of a communication system? So here AI can be on the base station, AIs can be on the phones. The value add or the challenge is when there has to be AI models on the base station as well as on the phone, which has to be interoperable. So, say for example, some company XYZ, which is a UE vendor, they come out with AI model, and then it works well with infrastructure vendor A. But the same model with a it's not guaranteed that the same model will work the same way with the different network equipments coming from different vendors, and the same vice versa. So that is where the two-sided models, how do we test? So this was problem statement. And then here we worked together with Qualcomm. So they had, for a use case, the channel status indication, CSI. So these are pilot signals on which the phone will do the measurements on the downlink signals and then will provide the measurement reports. So pilot meaning it doesn't carry any user data, meaning to say the operator does not make any money, but still, if we talk about spectrum efficiency, it is consuming some energy, some spectrum. So if we can reduce the number of pilots, so then I can have a better communication system. That is the idea behind. So for this, Qualcomm, they designed their own AI model, which goes into a AI, which goes into a chipset, which goes into a device. And then likewise, from R&D side, we developed a network side model, and then we interchanged. I mean, we gave our data trained model to Qualcomm, and they looked into how the model was trained, and then further we could see, I mean, after some fine tuning between the two models, we could see some significant gain with less pilots transmitted. We were able to eliminate some of the pilots which otherwise had to be transmitted. Yeah. So what they did address, one, AI models can be tested. Two-sided AI models can be tested with this methodology, and based on this, the 3GPP, they took it as a study item, and then now it has been, like, say, as part of the studies ongoing within the 3GPP. So likewise, custom constellations. So we know all the constellation diagrams, the modulation schemes. So right now we have very static representation. That is, the symbol representation is very static, and in between I have to insert pilots. So what happens if I have a AI learned constellation, which is custom pseudo in a pseudo random looking constellation diagram? Yeah. So like this. So it need not be like very static representation, but wherever the channel is good, so the learned machine learning AI model will say, this will be my custom constellation on the transmitter side, and then I communicate this to the receiver saying that, okay, how about using some of the uh, symbols here for pilot, and then this is the best way of sending data from the transmitter to the receiver. Then also I can reduce or cut down on my pilot transmission. Yeah? So that is some test bed which we have also worked together with the NVIDIA neural receiver. And here we see, so this was the signal to noise ratio required for without AI, 5 dB SNR required to achieve a certain throughput. So now with such a custom constellation, I was able to reduce the signal to noise ratio to down to 2 dB. So this is my actual performance, which is very close to my theoretical value, maximum likelihood. Yeah. So this is towards working towards a pilotless communication, that is less reference signals transmitted from the base station to the UE and less reports being sent from the UE back to the base station. So this was one objective. And then how good is this neural receivers? So I have the AI training, machine learning, AI models, I have new receivers. So how good is it performing in real network or different geographies? So that is where digital twin comes into picture. So here in digital twin, what happens? So here is a video. Say, for example, you will have to consider the antenna characteristics of the transmitter. Say this is my base station. I hope you can see my pointer. So this is my base station and these are my two receivers. The two UEs, one is a car, maybe another one is a drone. They are moving along different paths in a city in USA, and I want to recreate this channel conditions in a lab. How good is my implementation, receiver implementation with all these AI features? How does it perform in a real environment? So that is the purpose of digital twin. So with this software coming from ANSYS, we can model the channel conditions and then bring it into the lab. In the lab, we have a fading simulator called the SMW200A, wherein we can superimpose the 5G signal onto the channel conditions and then recreate that USA scenario or some factory scenario in a lab. So that is digital twin. And also there is one more project which I want to highlight here, where Nokia Bell Labs, they were working on a receiver where they were implementing a feature called digital post distortion. So normally we know on the transmitter side, what is the most complex or limiting factor is the power amplifier. So power amplifier, I don't want to drive it into the saturation. So that is why I want to operate the power amplifier continuously in a linear range, for which I normally need a closed feedback back from the receiver to the transmitter so that I can fine tune my power amplifier. So now with machine learning and artificial intelligence on the receiver side, that is the receiver path on the base station, can have something called as digital post distortion. That is, I have some machine learned AI model which looks into the pattern of the signal received, and I automatically correct for the non-linearities of the transmitter side. So this is what can be future receiver architectures which you can see in field. So there we are also offering solutions to test those kind of neural receivers. You can bring your own AI models, and then inside our spectrum analyzer, normally we have our own receiver chain. You can bypass that and have your own neural receivers and test the performance of those neural receivers. That is the idea behind. So we have done this kind of testing in some summits as well. I'll pass this information or slides to you later on, so you have this for ready reference. That was about AI run. Then next, coming to FR3 and GigaMIMO. So here, all I can say is this is a golden band. Why? Because it offers the same coverage as that we get with the FR1 frequency range. And yet, so here with FR3, the same aperture size, I can have more antenna elements. So from massive MIMO, if I'm using FR3, I can have more antenna elements, thereby my capacity, network capacity also increases. So with FR3 frequency range, I can achieve the coverage of FR1, capacity, what I can get with FR2. So that is why this is a very interesting frequency band, which most of the industry is looking into. Yeah. So these are some tools which we use to measure the characterization of the device or the antenna, phased antenna arrays, and also the reconfigurable intelligent surfaces. So to measure that, so here this is the chamber, for example, inside which you can position or put your RIS device or say FR3 capable antennas, phased array antenna modules. And then you have inside the Qatar compact antenna test range, so which can transmit the signal, and then the beams which are reflected from the RIS module, or say the beams which are coming out from the phased antenna arrays, can be measured using the other Qatars within the chamber. So this is a very small chamber which can fit into a room, and it's on wheels, as you see. So it can move from one room to another, and then inside a lab you can test the RIS performance or the phased antenna arrays which are operating in FR3 frequency range. Yeah. So with that, well, let's look into the last item, which is the integrated sensing and communication. So the concept behind, so here I have a transmitter on the ground, receiver on the ATC, air traffic control, and in between I have a helicopter with rotor blades stagnant. And then here you can see the signature of the RF signal. Now I ask the pilot to switch on the engine, the rotor blade starts rotating, and then you can see the variation in the RF characteristics. The signature changes. This is the basic concept behind integrated sensing and communication. So we have today thousands of base stations which are already installed, operating in frequency range 1. And then if I can sense the objects, the environment around me, then I can address several use cases. Say, for example, the drone detection, and also finding the path which the drone is taking. It can be a good drone or a bad drone. Good drone is like the medical drone, which will offer assistance in case of a landslide, or maybe a bad drone is an enemy drone which is coming into our region. So such examples. Or maybe say, for example, I have a router or a CPE inside a house, and I can, as soon as somebody illegally gets into the house, I can sense that using the network. Or in case of a smart factory, the AGVs which are moving around in the factory, they don't collide with each other. The same applies with vehicles. And also, say, for example, I can use it together with RIS. Say, for example, the base station will detect there is a block or a wall which is blocking my signal. I detect this, I sense this, and then I fine tune or change the direction beam steering to a RIS, which will then reflect the signal to a different area behind the wall, serving more users, which otherwise was not possible. Combination of ISAC and RIS. Yeah. So these are some of the use cases, and there are multiple architectures. Say, for example, who is going to do the transmission of the signal, who is doing this sensing. So here on one end, I have my transmission, on the other hand, I have my reception. So TRP is my base station, the trans receiving panel. So here, if my TRP is sending a signal and detecting a target, it hits a target, and I get my signal, reflected signal, and then I do the sensing. So this is a monostatic scenario, uh, base station based monostatic scenario. Likewise, UE based. Say, for example, UE is sending a signal, it hits a target, and then the same signal is sensed by the UE, monostatic UE based signal. Or if you are using multiple base stations to sense the signal, then it is a bistatic or multistatic scenario. Multiple scenarios are there. So now what is the specialty? What are the challenges? What are the additional things I need to consider when deploying an ISAC enabled network? So for the communication channel, we know we characterize the communication channel based on the throughput, voice, video quality, RF performance, the EVM, the power spectrum. Now with this kind of sensing, say this is my object and this is moving, and this can be of different sizes. So the new attributes could be the distance at which this object is compared to the base station, and with what velocity it is moving, whether it's approaching the base station, moving away from the base station, and what is the size. Size means RCS, radar cross section. So these are the new attributes, and how I characterize this sensing channel is how accurately detect this object. How accurately could it resolve? Like, for example, bird, and then there is a drone. How can I differentiate between a bird and a drone? Yeah, that is the resolution. So these are the new KPIs which a communication system which is enabled of sensing has to take into consideration. For that, here I want to introduce one instrument which is the REC, which simulates the different targets like the car or a drone or a pedestrian of different sizes, and as if it is moving at different velocities, that can also be configured within this box. So this kind of box, if you have it in a lab, you can test a sensing enabled base station performance and the accuracy, the resolution sitting inside the lab. You don't have to go into the field every time to test such scenarios. Yeah, that is the idea behind. So here we did an example test bed inside a meeting room, as and when people, so for example, starting, this was my RF power level. As and when more people came in, there was more attenuation. So on one side is my transmission signal from Docomo, and the other side I had that ISAC target simulator. And then as people came inside the room, there was more attenuation I could sense, and thereby I can see, okay, more people are coming into the meeting room. And as more people go out, and then maybe the lights will switch off automatically, something like that. Or say, for example, with Nokia, we did one in a smart factory. So here we had Nokia base stations, which are capable of sensing. And then on the other hand, we had the target simulator, the REG, so where we could simulate multiple objects, and we are checking the accuracy with which the Nokia base station could detect the multiple objects. So that is what we see in the different graphs here. There is a press release on that as well. And then, currently, what is the status within the 3GPP? So here, ISAC, in order to be truly integrated sensing and communication, currently, of course, we are using the same OFDM based, new radio based waveforms, but can also look for waveforms where there's a tight integration between the sensing and communication. Yeah. the main, say, for example, radars have existed for quite a long time now. And likewise, the terrestrial networks have existed for a long time. What is the main motivation behind enabling the communication system to sense is one, we have thousands of base stations which are already deployed. And then the deployed network is never used to the fullest 100%. There is still some room and be used for sensing. And with an optimized waveform, which has which can accommodate sensing as well as communication, and with a good trade-off, like say whether I do more of sensing, then the communication capacity will go down, or if I do more of communication, less sensing. So this can be defined. Yeah, this can be addressed with the different waveform types, and of course FR1 GPP now, and it's not only about detecting the object, and it's also about tracking. So drone enters my region. It's not only about detecting it, but tracking that drone, for which the base stations need to talk to each other, send their sensing reports to neighboring base. So which means I need an open interface and might play a role here. Yeah. So these are some ideas I wanted to provide with regards to ISAC. So in, say, for example, in the next generation networks, it will be a multi-layer, multi-dimension network operating in multiple bands. As you can see, have non-terrestrial networks operating in different orbits, terrestrial networks, the different use cases, and also personal access networks, like say the UE, the man, a person with all his gadgets connected. So all of them are sharing and working in uh, cohesively. So that is the vision behind. And AI will play an important role behind all this. And already we are working together with a lot of research institutions worldwide across the globe. We are also a part of a lot of alliance like the Bharat 6G Alliance, the ORAN, AI RAN Alliance, and so on. So yeah, the call for action today from my end would be, let's work together to enable the research ecosystem in India to address the different use case in India, and we are always happy to serve, make your ideas real. I come to the end of my presentation. Over to you, back to Asta ma'am.
Yeah, thank you, Mahesh. I think very informative. In fact, first time I learned a lot, so I'm sure that this is useful for the other members as well. So we have come to the
Yeah.
last question answer, and I request the audience to ask their questions in the public chat, which will be taken by Mr. Mahesh one by one. But right now, I see one hand raised by Mr. Padum. So I think I request you to just please raise your issue.
Yeah, thank you, sir. Thank you so much. Uh, Good afternoon, one and all. My question is a wonderful 6G part. As the institute is concerned, and would like to MOU with your company for the joint collaboration research. How could you initiate that part? Can you please put on some light on that part?
So we can get in touch with each other, and then I've given some insights about the areas we are working on, some solutions. Of course, I did not make it a product promotion presentation, but I can also, like say, we can have a one-to-one conversation where we can see what are your requirements, what are the use cases you want to address, and then yeah, it's on a case by case, touch, know each other's use case solutions, and then get into an MOU. And we have a big R&D center here in India with over 300 people work technologies, and I'm sure we'll be able to find a way to establish a collaboration. So we are always open. You can take my email ID and get in touch with us.
Okay, thank you.
I see another
Thank you.
hand raised by Mr. Tripathi. And
Yes,
then
sir.
one question you can see in the public chat by Abin Bade. So you can just take up those questions.
Yes, sir. Sir, you have
Yeah, one
talked
is
about. Yes, I am Tripathi. Yes, just asking the question.
yeah,
Hello, I'm audible,
Yeah,
sir.
please go ahead.
yeah,
Yeah,
Yes.
yeah.
So my
yes,
question is that in 6G
I've
RAN case, you talk about the one-sided model and two-sided model. The one-sided, two-sided model was like AI at UE end and AI at transmitter end. So there was a
mhm.
vendor issue you have mentioned. So how the industry is going in which direction? Because that a very lot of vendor dependency is there, as you mentioned. So how to resolve at large scale this thing in future?
So, of course, none of the specification or the standardization bodies will come and say, this is the exact blueprint, how you have to implement the AI models, how you have to program, how you have to come out with an AI model. So, definitely, this is a challenge within the now. So, that is where we have done the first like collaboration with Qualcomm, where we went from the network side using our instrument where we could load our network side decoder. The encoder was on the UE side AI model, and then we checked on the interoperability and then fine-tuned some parameters so as to achieve the maximum performance. So this will still be the case, like say the whole industry, like say it can be the Ericsson's, Nokia's, or anybody on the network infrastructure side. Their models, they want it to work seamlessly across the different chipset vendors, device vendors. And now this is not limited to phones or PCs, but also with the physical AI coming into picture. It can be robots and so on. So right now, this is a one-to-one collaboration. They need to work together, but how it will be done is still a question mark. We have given the first blueprint, like say working together with Qualcomm about, yes, definitely it can be tested, but how to scale this, that is still a question which we should be able to find answers within the AI RAN Alliance, where there are some guidelines. So there can only be guarding guardrails for how you use the data, synthetic data or real data, and train your models. So this is still work in progress, I can say, Mr. Tripathi. Yeah.
Sir, got it. There a follow-up question you have just mentioned that there a collaboration with this uh, Qualcomm. Yeah, CSI number of pallet signal you are reducing. So
Mhm.
it's a reduction means in percentage term. Can you elaborate how much this reduction is there in number of pallet signal?
This maybe we'll take this offline because it will be a detailed one, and I can
Yes,
pass you some information like papers on how
yes.
we did this. Yeah,
Uh,
yeah. In the interest of time, let's do that, Mr. Tripathi, if you
Yeah,
don't
okay.
mind.
actually, one
Just
more
share your mail
question by
ID.
Mr.
Yeah,
Yes, sir. Just share
Abhinavade. And
mail.
then, in fact, we'll be sharing, sir. We'll be just sharing all the details to all the
Okay.
participants. We have all your details here. We'll be
Mhm.
yeah,
sharing you his number as well.
Okay,
And
sir.
yeah.
Mr.
My
Abhinavade has one question in the public chat. You can respond it, and then we can close.
yeah, sure. So. Mr. Abhinabade, he mentions query what could be the main spectrum for ISAC deployments? Will sensing work well in FR1? Very good question. So the last but third slide, I mentioned this. So the main spectrum right now, the priority is FR1, and the resolution of the object detected will of course be better with higher frequency like FR2. But as I mentioned, the advantage with using my existing thousands of base stations which are already deployed, they are all working in FR1. So that is where AI comes into picture. Like for example, I take a picture with my camera with a low resolution. I use some AI tools to enhance the quality of the image. So the same way, the sensed objects at FR1 with lower resolution can you make use of AI to improve the resolution further using AI? So that is my answer to your question. So this is something which is a practical problem and it has been addressed that way. So that is where
Thank you.
AI comes into picture. Yeah.
Thank you. Now we have given already, Mr. Mahesh has given his email in the public chat, so anyone can note down the chat and directly take up the questions. In addition, these all the today's presentations, is available on YouTube. The link has been given above, and all other even 6G Tech Talks are also on the Bharat 6G Alliance YouTube channel. So anyone can use them, including add them in their LinkedIn post as well. So with this, I would like to thank you from Bharat 6G Alliance and invite Astha, our assistant director, along with the Swapnil and Faisal for the vote of thanks. Over to you, Astha.
Yes, sir. Thank you, sir, for providing me this opportunity. On behalf of Bharat 6G Alliance, it is my privilege to propose the vote of thanks. We have had an insightful and forward looking session today. The discussion on the evolution from 5G advanced to 6G has truly highlighted the scale of transformation ahead, one that is not just about faster connectivity but also about building intelligent, resilient, and deeply integrated communication systems. The slides which were you shared was a very interesting and very like lectures I'm hearing and seeing. I was learning a lot about the NTN space and the terms like motion to photon latency and all the new aspects which you shared, the innovation areas. So I would really thank our speaker for today, Mr. Mahesh, for sharing such a comprehensive and thought-provoking perspective. My heartfelt thanks to our Patak sir, DG, and David sir from Chairman of Parasector Alliance, to our organizing team, Swapnil and Faisal, for helping us enabling this session to be organized and work diligently, and also to all the participants who have put forward such interesting questions and the insightful discussions which we had. We always look forward for this Q&A session because this give the feedback to the speaker as well. With that, I once again thank to our expert speaker and all the participants for making this session a great success. Thank you and have a wonderful day ahead.
Yeah. Thank you very much for the
Thank
opportunity.
you all.
Namaste.
Thank you. Namaste. And we will again meet on next 25th of June when we are bringing together a session, very informative session by Mr. Puneet Jain, Mr. Anil, and others on 3GPP release 19 and 20. So be ready for our next session. That is not on tech talk, but that is on something on 3GPP, how we do it on the 25th of June at 10:30 onwards. Thank you all.
Thank you. Thank you.
Thank you.